Good afternoon, everyone. Thank you very much for joining this afternoon's NITheCS seminar. It's a great pleasure to introduce today Dr. Mary Jane Bopape, who's the Senior Manager of Research at the South African Weather Service. She works on homegrown weather models and leads activities on weather and climate projects at the SADC Cyber Infrastructure Project. She's co-president of the South African Society for Atmospheric Scientists. And just in terms of background, in 2013, she obtained a PhD at the University of Pretoria, entitled Simulations of Moist Convection Using Quasi-Elastic Equations. She does numerical modeling of the atmosphere in space and time on different space and time scales, which of course requires significant computational expertise. Mary Jane, we're keen to hear what you have to tell us this afternoon in your talk entitled Forecasting at the South African Weather Service. Please go ahead.
Okay, thank you, Christian, and thanks to you, Renee and Ilya, for inviting me to come and speak here on work that we are doing at the South African Weather Service. I will just ask that you confirm that you can see my screen okay?
Yes, we can.
Yes.
Thank you.
Okay, thank you so much. So I will be speaking to the forecasting that we are doing at the South African Weather Service when we consider different time scales. As the South African Weather Service, we are an entity of the state, and our mandate is to provide weather and climate information. And for us to be able to do this, we have to make a whole lot of, collect observations across the whole of South Africa. And in 2013, our mandate was extended to also include air quality. So in addition to, obtaining, meteorological information, we now also obtain air quality information. As an entity, we also have some designations from the World Meteorological Organization. So in the way that we do things, we do follow, guidelines of the WMO, World Meteorological Organization. And we're a regional specialized meteorological center, which means our responsibilities are not just for South Africa, but they are also for SADC, so for Southern Africa. And we are a global producing center for long-range forecasts. So this just means we also produce forecasts globally for the season. And we are also a regional training center, which means with the meteorological training that we provide is not just for South Africa, but we also provide training to meteorological services or meteorological organizations within SADC. So in terms of the way we work, so our forecasting, we deal with weather, we also deal with climate. And the reason why we are able to separate those is because we deal with different time scales. So the WMO, the World Meteorological Organization, defines time scales as going from nowcasting, and we go all the way to multi-decadal, climate change projections. And as such, we do try to cover all these time scales. We've got what we call nowcasting, which goes up to 2 hours. We have short range forecasting, which goes up to 3 days. We have medium range forecasting that goes up to 2 weeks, and we have seasonal forecasts, which are generally 3 months means, and we have multi-decadal projections that we also conduct. So the way that my talk is structured now is I'll speak to the time scales from nowcasting, just showing you what we are doing at the South African Weather Service, all the way to the multi-decadal work that we are conducting. And as you can see, so that figure shows that as we go and we increase the lead time, that forecast uncertainty increases. So for our nowcasting, the most important tool that we have at the South African Weather Service is a radar. So we've got a radar network that covers most of South Africa. You can see it's parts of the Northern Cape that are not covered there, but that's because we don't have a lot of thunderstorm activity that is taking place there. You see bigger circles there in green. Those are our C-band radars. There are older radars that we will hopefully be able to replace once we have the funds. And the other circles there, the yellowish or orangish color that you see there, those are our S-band radars. They were deployed in 2010. So the South African government spent 240 million to buy those radars. So with the weather radar, we are able to get a three-dimensional view of what is happening in the atmosphere. And our main interest with these radars is really getting information on thunderstorms. So most of the rainfall activity we get in South Africa is of convective origin. So that means things can happen quickly and changes can happen really quickly. And so we need to be able to warn the public. I'm showing you two figures there with a black background, and you can see some red colors somewhere, and you can also see a cyan color that is shading, that is around some bright colors there. So that is reflectivity that we get from radar, and from our radar we are able to now be able to say this is the direction that the thunderstorm is taking. And when that happens, our forecasters are able to warn the public. I'm also showing an example of what we get of what our forecasters issue on Twitter to the public to tell them that there's a thunderstorm that's coming in their direction. So this type of work does not require a lot of computational resources, so we can do this just with a small server. So we don't really need high performance computing facilities to be able to do our nowcasting work. Then as source, we also have a lightning detection network. So we have 24 sensors. They are based on Vaisala. It's a company in Europe. We have 24 sensors across the whole of South Africa. We are also using a sensor in Swaziland. So our sensors are based on its magnetic direction as well as time of arrival. So when a lightning occurs, we are able to pick it up in near real time. These sensors were deployed in the year 2006. So we do have a bit of a terminology. You can see there the number of strokes or the number of flashes that were picked up by this network from the year 2006 up until now. So we do have, we would expect most of the activity to happen in the eastern part of the country, and you can see that is what this network is observing. So our lightning detection network is actually our most reliable network when it comes to observing what is happening in the atmosphere. We are also relying on satellite information. So the one that we are relying on at the South African Weather Service is Meteosat second generation. We are relying on the geostationary satellites. So with satellites, you've got satellites that are orbiting, and when they orbit, they would pass maybe one area twice in a day. While with geostationary satellites, they are able to make observations in near real time. So the one that we are relying on, this MST updates us every 15 minutes. And that means that we can track what is happening with thunderstorms. So when radar is our most reliable, it's the one that provides us with the most useful information. Information from satellite is also useful. But where you do not have radar coverage, it's good to have information from satellite. The figure that I'm showing you there is showing you the thunderstorms as they are occurring. They are in different phases. Some are growing, some are mature, and some are decaying. And for this, we have information that is available for South Africa, and you can see that we also extend this information up all the way to the equator, so that our neighbors who don't have radars, most of the countries north of us do not have weather radar, so that they can also use this information. So with this information, the forecasters in different countries can be able to tell this is what's happening in terms of thunderstorm activity, and be able to predict going forward. So the website that I'm showing you there is what we give to the Met services within the SADC region, so that they can have access to this information. It comes out of a software which is called the Nowcasting Satellite Application Facility. And as far as we know, the South African Weather Service is the only one that has been able to install this software. Then when we move, so what I've just discussed is up to nowcasting. So now when we start moving into the very short range forecasting time scale, we start combining information from numerical models with information from satellite. We have what we call a flash flood guidance. We've got a Southern African regional flash flood guidance, which is available for a number of countries within SADC. And it uses precipitation information that we get from radar, so from satellite. From the satellite information, we come up with quantitative precipitation estimates, and that information is then used in this flash flood guidance. It's not a system that we developed here in South Africa. It was developed in the US, so we just provide input data as well as from the models, as well as the quantitative precipitation estimates that we get from our satellites. Then the Met services will know which basins are most likely to flood in the next 6 hours. For South Africa, we also have the South African flash flood guidance, and for that one, we use quantitative precipitation estimates that we obtain from radar. So that means it provides us with higher resolution than what is available from what we get from radar. So I'll move on now to another time scale. So for us to be able to say anything really from beyond 2 hours, we have to use numerical models. So our numerical weather as well as climate models are based on the physics really. So we rely on conservation of momentum. So we've got an equation that takes into account, for example, the Coriolis force, which speaks to the fact that the Earth is rotating, that takes into account the pressure gradient, the movement of air from where the pressure is high to where the pressure is low, that takes into account buoyancy, upward or downward motion. So that will speak to the conservation of momentum. Then we've got conservation of energy, which speaks to the energy coming from the sun, the reflection, as well as, the long wave radiation that would leave the surface. And that equation will then also include, if we were to project going forward with climate change, that would include heating that is associated with the anthropogenic greenhouse gases. Then we also have, conservation of mass, so the continuity equation that we also solve. So all the numerical weather and climate models that we use are really based on these three equations that I have mentioned. In terms of HPC resources, for us to be able to run these models, we at high resolution, and for the information to come out timely so that we are able to warn the public in time, we have to run on HPC resources. I'm showing you an example there of the South African Weather Service CRAE system. It is an XC30, so it's an older system that we are trying to replace at the moment. It has 168 nodes, so these are based on Ivy Bridge processors. And in terms of the high-speed storage, we've got 1.7 petabytes of Lustre storage. And on this system, we are running a model, a numerical weather prediction model called the unified model. The model runs over the whole of SADC. So there is another figure I'm showing you here, this figure one. So it shows you the domain that we are running. So we are running this model every 4.4 kilometers. There is a calculation that we have to make. And for this, we use 1,728 cores of the CRAE system per run, and the model would run for just over 1 hour to produce 72-hour forecasts. Then the small one that you see, which is just over South Africa there, we are running this model with a grid length of 1.5 kilometers, and the longest lead time that we have is 48 hours. So we run a model with some really small time steps, and then after 48 hours, after the model has produced 48 hours of simulation, then we stop and we run the model in the way that we write the output. We write the output for every 1 hour. If you go to big centers such as the United Kingdom Met Office, you'll find that they've got duplicate systems that they will use for failover. So we have to forecast weather every day. And even if our machine fails and there's some high impact weather system that is coming through, we need to be able to forecast it. So for this, we are working with the Center for High Performance Computing. We've got a memorandum of agreement with them that says, should our CRAE experience technical difficulty, we will run the forecast, but just the 4.4 kilometer one on their system. So this is just an example of the type of output that you can get. So you can see that line, the black line there is showing you Gauteng. So out of the model, you can get output, you can get precipitation, temperature, winds. The example that we are showing you there is reflectivity. It's basically for us to be able to compare what the model produces with what the radar is showing. But another thing, that the message that we are sending with this slide is to indicate that there is uncertainty that is associated with these models that we are using. So for us to deal with that uncertainty is that for each forecast that we make, we will produce multiple realizations. With this example that I'm showing you, it can see it goes from 1 up to 18. So we made simulations where we perturbed, we got information actually from the UK Met Office, where we made simulations for the same period. And out of those, then we can produce some probabilities that will then give our forecasters confidence when they issue warnings. So we don't want to miss events, and at the same time, we don't want to send out false alarms, because that can also cost money. Then in terms of the uncertainty that is associated with models, models perform differently, across the continent. But all in all, we think the model that is run by the ECMWF is basically a European Union center that tries to make forecasts for a number of European countries. It has the best model in the world, but all in all, science has shown that when you combine forecast output from different models, you get better skill. So at source, we also get information from models that are run by other centers. The example that I'm showing you there is a multi-model ensemble prediction system. We run only the unified model. So it's the one that is showing the way it says SA4. We also get information from a model that is run by the Met Service in Germany. We also get information from the model, the global model that is run by the UK Met Office, as well as the one that is run by NOAA in the USA. Then we combine all that information. Again, it's so that the forecasters can have confidence in what they issue. So I'll move on now to the seasonal forecasting. So the work that I've just discussed now is really, so for us to get good output, what you need are really good initial conditions. So we need our observations to really provide us with good information for us to be able to forecast going forward. Then with seasonal forecasting, because now we are looking beyond seasonal forecasting, we look at about a 3 months period. We rely on usually slowly evolving boundary conditions. So we know, for example, that the sea surface temperatures would leave some memory in the atmosphere that will make the atmosphere predictable. Some of you may have heard of the El Nino Southern Oscillation, which refers to what is happening in the equatorial Pacific Ocean. So when sea surface temperatures in the equatorial Pacific Ocean are above average, we get what we call El Nino. And generally for Southern Africa, we get below normal rainfall. But when we have got La Nina, which is where the sea surface temperatures are below average, there in the equatorial Pacific Ocean, generally for Southern Africa, we get above normal rainfall. And that is what is happening at the moment. We have got a La Nina. That figure that I'm showing you there is actually fresh. We haven't issued that at the moment. We ran the model, which gave us updates. The model was last updated on the 18th of November. So we'll hopefully issue the forecast sometime this week. And where we see, so with the two maps that are showing just South Africa, so it shows that this is a forecast that was issued in November for DJF. So that DJF refers to December, January, February. So it's 3 months. And again, issued in November now for January, February, and March. Then the brownish colors would say that we are expecting rainfall to be below normal, while the greenish colors will say we're expecting rainfall to be above normal. And you can see for most of South Africa, we are expecting above normal rainfall. And this is because the models react very well to what is happening in the equatorial Pacific Ocean. We are in a La Nina state. That is why the models are indicating above normal rainfall. Then I indicated that we have got a status as the Weather Service of long range, as a global producing center for long range forecasts. So I'm also showing you a map that indicates that we produce forecasts, seasonal forecasts for the whole globe. But in terms of what we issue ourselves, so this information is available for different net services to use to issue forecasts for their countries. Then again, we've got uncertainty that is associated with different models. So while we are running our own coupled model, we also obtain information from other international centers. So in our case, we are using models that are run in North America. From it's 2 models that we add. Therefore, we combine 3 different models to be able to produce the 2 maps that I'm showing there that are just for South Africa. We are now in the process of trying to extend this ensemble forecast. So as I mentioned, so from the work that has been conducted, the more models you include, the better the forecast. So we have 3 at the moment, and there are some centers on the continent. There's one called ICPAC in Kenya that uses 10 different models. So we'd like to get to that level as well, where we use many models so that we improve on the skill of our forecast. Then I mentioned that we also produce output. So just looking at the multi-decadal projections, the South African Weather Service downloaded data. So I'm sure, I don't know if some of you might have heard that there is a report, Governmental Panel on Climate Change, a report that was issued in August that indicates that there is more compelling evidence that shows that our activities have increased the concentration of anthropogenic greenhouse gases, and that the extremes are changing because of this change in the concentration of greenhouse gases that changes the climate system, which also then changes the extremes as well. So the South African Weather Service is also working in this area. We have, initially, we were just downloading models that were run elsewhere, but now we are working with Professor Francois Engelbrecht, who is with WITS, with the Global Change Institute, to do some dynamical downscaling. So we have a number of centers that would run projections over the whole globe, but the resolution that you will get with global models is not as high as we would require. So for us to be able to get high resolution, we will then run a model with higher resolution over an area that we are interested in. So that is the dynamical downscaling that we are working on with Professor Engelbrecht at WITS. So what I'm showing you there with RCP 8.5, RCP 4.5, the RCP means representative concentration pathways. So these were used for the previous assessment report, the assessment report 5, and then there are newer ones for assessment report 6 that we are working on producing. We also conduct some research. The one that I will speak to is one that we're collaborating with a number of countries within SADC. We got some funding through the Climate Research for Development Fellowship. It's CR4D, and the CR4D Secretariat is with the UN's ECA, so the Economic Commissions for Africa. They've got a center there called African Climate Policy Center. They gave us some funding, $100,000 for us to do some research. And we worked with Botswana, Mozambique, Namibia, Tanzania, as well as Zambia, with South Africa leading the project. And we also collaborated with NASA, UK Met Office, as well as University of Reading. And the focus of our project was on modeling. For us to start our research, we did a situational analysis for member countries. We wanted to find out what is happening. Are they running models? So from what I've just showed you, you can see that for us to be able to forecast going forward, we are relying on models. So we wanted to find out which countries are running models, and we found that there were 3 different models that were running. However, in terms of capacity, there was very limited capacity because many countries do not have high-performance computing systems. Sometimes they would be running models, but they will use lower resolution. So a limited area model that runs just say over one particular country will run with lower resolution than the global model that is supposed to provide information to it. In terms of seasonal forecasting, we found it was only South Africa that was running a coupled ocean atmosphere model, while all the other countries were doing some statistical downscaling. So that informed the research questions that we knew we had to look into. So what inspired the project was the fact that we knew that the Center for High Performance Computing was working in collaboration with a number of these countries, together with the SADC Secretariat, to deploy high performance computing systems in different countries. So the image I'm showing you there was published in our 2019 paper there that showed different countries that had HPC systems. So we wanted to work with these countries that had HPC systems, and you can see where you see a red sign. These are the countries that were part of the project that I mentioned. We ran some workshops where we gave training on the implementation of the weather research and forecasting model. So it is a famous weather model that is used in a number of countries. And we basically ran different workshops. So in the one, the model was being implemented. In the one workshop, different scientists were now presenting on the heavy rainfall event simulations that they had performed. Then we also got application scientists. So these are people that take the weather and climate information and try to use it to make sense for, ask questions around what are the implications for agriculture, what are the implications for the water sector, the energy sector, health, as well as for socioeconomic benefits. So in terms of research questions, we looked at the structure of an atmospheric model. So I should probably have put the slides earlier on, but the way we name our models would depend on the resolution that they are used, the resolution that we use. We've got global models that if you were to use really high resolution on them would be really expensive to run. Then we also have regional models that will run just over the area that you are interested in. Then as we use higher and higher resolution, we get to a point where we start resolving clouds, and there we have models that we call cloud resolving models. So those models, generally you would want to use a grid length of about 4 kilometers or less. Then as you use higher and higher resolution, perhaps even getting to about 100 meters, then we start getting large eddy simulators. And the reason we say it's large eddy simulators is because with that type of grid length, you will be able to resolve large eddies. So large eddies, they scale with the height of the boundary layer, and the boundary layer height is about 1 kilometer. So different countries ask different questions. So we're all using one numerical weather prediction model. And for South Africa and Namibia, we asked questions around what are the implications of using different resolutions. Then for Mozambique and Tanzania, there were questions that were being asked about the sensitivity to deep convection. So what the model is not able to resolve explicitly, we use what we call parameterizations. So they basically consider the relationship of the subgrid process that you are not able to capture with what the model is able to resolve. So deep convection is one of the areas that we know is associated with uncertainty in our simulations. Then Zambia looked at sensitivity associated with the planetary boundary layer schemes, while for Botswana, we looked at sensitivity that was associated with cloud microphysics schemes. So overall, in terms of the observations, so for all the 6 countries, we were comparing different observations. So Africa, in general, as a continent, we've got sparse observations. So if you look at what's happening in the US or in Europe, you'll find they've got a lot more observations. In terms of radar coverage, they've got a lot more than what we have here on the African continent. So in the end, we have to rely on different, on different sources of observations. We have to rely on satellite information, and there are different products that are available. That figure that I'm showing you there, so A is station data that we got from the Botswana Meteorological Center. Then B shows you a NASA product. So that is supposed to be observed rainfall on a particular day. It's 18 February 2017. So this was following the tropical cyclone Dineo. So the system continued all the way and caused heavy rainfall in Botswana. Then the one that you see, which is C, it's ERA 5. So these are the reanalysis. So again, these are considered as observations. Then the one that you see, there is TAMSAT, that is the University of Reading product. So all of these are observations, and they are saying this is what has happened on that particular day. The color scheme is exactly the same. And you can see that what we are reading in is very different. So if I am to run my model and it produces what is shown there in D, I would say my model has performed well, or if it's so it's basically a question of if we don't really have enough observations on the ground as modelers, what should we be targeting? So for the African continent, there's very little progress in terms of improving the skill of models, and you can see where the challenge is coming from. Obviously, A represents the somewhat, you could say, is the ground truth, because those are the actual ground observations that we had. In terms of the modeling experiments, we found that the cloud microphysics, or changing, different schemes, with the cloud microphysics and planetary boundary layer schemes, there was not much in terms of the simulations, differences in the simulations. But when we switched on and switched off the convection scheme, we found that there was a big difference. So the cloud microphysics schemes will represent processes such as condensation or ice turning into cloud water, that type of information. So it didn't, so any scheme that we use seemed to work almost the same. And then with planetary boundary layer schemes, they would look into mixing, especially in the boundary layer, but some of the schemes will also consider the effect of shallow convection on mixing. While with the convection scheme, we try and represent what is happening with this big thunderstorm, on the impacts on the stratification of the atmosphere, and then they also have as a byproduct rainfall, which is why we are comparing rainfall here. So switching off, so I'll show you just with this one example where you can see my arrow, you can see where inside this the red line there, we had switched off the convection scheme. Outside we have not. So when you've got the convection scheme switched on, even at these high resolutions, you don't get the benefit of high resolution. We have to switch off the convection scheme in order for us to be able to capture some of the intense activities. So we published a number of papers. So to get more information on the sensitivity tests that were conducted, you can visit some of these papers. So I mentioned that our mandate was also extended to include air quality information. So we also do air quality modeling. So with air quality modeling, you can run these spatial models where you provide information, meteorological information from numerical weather prediction models, but you can also do some really coupled, some intensive modeling. So at source, we do this intensive modeling, but for this, we are not yet using our in-house HPC system. We are using the CHPC. I'm just showing you, so what's busy moving there, those are the fires, and as you get fires, you also get biomass burning. There are some gases that get produced, even just, when you look at the natural vegetation as burning is taking place. So there are some gases that will be produced. Then you will also have something that comes of dust. Then, with all that information, so you will get information that comes from nature, and then you'll also get information. Sometimes different municipalities will take observations of what the emissions are from different sectors, from the energy sector, from the agriculture sector. And then we take all that information and then we can input it into some of the models. So I'm showing you there an example of a trace gas continuity equation. It takes into consideration, motion, vertical, horizontal as well as vertical motion. It takes into account dry and wet deposition. So that's just, the sources. Wet deposition would mean it's raining and therefore kind of cleaning the atmosphere. Then it will also take into consideration the chemistry. So out of that information, we can then be able, so we are running this model just for South Africa and Southern Africa, and we also have a model that is running with a grid length of 20 kilometers for the whole of Africa. And for this, as I mentioned, we do need an HPC system because it's so running this is more expensive than just doing the weather and climate part. So because it includes both the weather and climate as well as now the chemistry part. So this information can be used, to assist with decision making. So that scenario-based air pollution management, the one that is seen there as 2, is work that we have done with the Mpumalanga province, where we are able to go and say, what if we were to reduce emissions for this particular sector? What would the atmosphere look like? So this is work that we have done with the province, and they were happy with the results. Then we've also collaborated. So basically, this is just to say air quality influences on our health, and we have worked with the Medical Research Council, where they've looked at the contribution of air quality to the burden of disease in South Africa. So the work was done just for the year 2012. So the work is currently under review. So as the South African Weather Service, we are not leading this work, but we hope it will make some headlines soon, indicating to us what is it exactly that is really killing South Africans. And air quality was found bad air quality was found to make a really big contribution. Then with COVID, we have made some contributions as well. So there has been indication from different parts of the world, that say people that have been exposed to PM 2.5, so these are just small particles in the atmosphere for long terms, they are at a higher risk of developing severe COVID. And so we were working with the government with different municipalities, so that they can just track and do their planning, as far as COVID is concerned. Then I'm getting towards my concluding slides. So here I just wanted to mention that we are working on model development. The models, so all the work that I've shown you now, where there were numerical models that were running, these are all models that were developed in other continents. And as South Africa, we want to contribute in the space and be able to develop models. And the way we decided to go about this was to work with a model called the conformal cubic atmospheric model. It was developed in Australia, and it has been in use in South Africa since the 1990s. So there are a few people that know this model very well, and we've decided to take this route of starting off with somebody else's model, because we've seen Norway does the same, and Brazil now has its own model, and the way they started was to start with a model that was developed in the US. So it will be difficult to say we are developing a model and just start from scratch. So we know this model has some shortcomings. Its data assimilation system needs to be updated. The cloud microphysics scheme also needs to be updated. So there are a number of things that we can work with, but we know the dynamical core is stable enough so that while other centers are busy developing new models, so this model doesn't really need to be developed from scratch. So we will be building capacity in South Africa on numerical weather and climate models using this model, and hopefully in the next 10 or 20 years, if a time comes where we have to develop a model from scratch, we will have enough capacity in South Africa to be able to do such development. Then here I just wanted to mention that at the South African Weather Service, so instead of saying this is what the rainfall is going to be, maybe we're expecting 50 millimeters of rainfall, we are moving towards being able to say this is what the weather is going to do, and we think that will assist decision makers in being able to make decisions. So if you say there's going to be 50 millimeters of rainfall, for some people, they don't know what that means. But if you say we're expecting some flooding and you need to move away to get out of harm's way, then it makes better sense to the public as well as to the decision makers in government. So we are also trying hard to reach more people in South Africa. So we wrote a paper where we were looking at the flooding that happened in KZN, where over 70 people died. So it happened around 23 April 2019. And we found that as the South African Weather Service, we did issue the warnings in advance, and yet we lost a lot of lives. And that is because our information is not reaching people that it should. So in some of our projects, we are working with community radio stations so that information can reach the public. We have got a weather app. We are also issuing, every time when there's an event that's coming, we issue a media release, a high impact weather event, we issue a media release. We've got an app through which we also broadcast our information. We are also interested in providing some programming training. So this we do perhaps as part of projects. So I'm just showing you an example of a training workshop we ran in February. We advertised the training the week before we're supposed to start. So we're running it every Friday of February, and we had over 100 people registering from 7 different SADC countries. So that just shows you that there are more people that are interested in learning programming. We're teaching basic Linux. We taught on Git and GitHub, on Python, on Fortran, and then we also taught on atmospheric modeling in general, as well as the conformal cubic atmospheric model, which is a model that, as I mentioned, we will be basing our model development on. So in conclusion, I did not mention the products that we develop, but so we have weather, climate, and air quality information. But in terms of the applications research, we've got people that are trained as agrometeorologists, we've got hydrometeorologists, we have people that are developing products for health, for the energy sector, and we also we inform the development of our products based on some socioeconomic benefit studies. We also have departments that are working on marine and aviation, so the development of products for these different sectors. And as I mentioned, we are interested in really doing model development research so that as South Africa, we can contribute towards solution development. And when we say the models are improving, we don't just wait for somebody to come and tell us these are the best settings for you, but that we can be able to tell all of that ourselves. So I think that is my last slide. Thank you.
Thank you very much, Mary Jane. That was really expansive in terms of hours up to decades, size scales from 1.4 kilometers up to continent and the planet. Thank you very much. And there have been various questions that have been asked in the Q&A and also some in the chat function. So I'll just go through those. Some of them seem to be, there seem to be a number of questions related to data and, how data that your measurements, that your devices measure are shared with other organizations, I suppose, if I can sum that up like that.
Okay, so I've just, so how do you want me to deal with this? Should I go with these one by one?
I think we can go through them one by one, yes, or I can just read the question to you if you want, but perhaps it's easier for you to read them yourself.
Okay, so I'll start with the first one. So it's asking about how granular can you go with your uncertainty quantification? What's the minimum scale can you go to? So it's I think it's a packed question because it speaks to how we are doing with different time scales. So generally, in terms of uncertainty, we can say the shorter the time scale, the less the uncertainty. So we do really well with the shorter time scales because we know what's happening. So the numerical weather prediction models that we are running at source, we update them 4 times a day. And as we update them, the forecasters will then keep updating the forecast because we know things keep evolving. But generally, when you get a really high impact weather system, like a cutoff low system. So when you have a big synoptic system, the models are generally really, they do a really good job in terms of capturing such events. While if you get some isolated thunderstorm happening somewhere in Limpopo, the models may actually be able to, they might miss that. So it depends on the system that you're looking at. It also depends on the time scale, but generally we say the shorter the time scale, the better. And then the smaller the system, well, we also don't do very well, but if the system it's really a synoptic scale system, we are generally really good when it comes to capturing it. But sometimes the models might struggle a little bit with really capturing the area where you would expect the maximum rainfall. But generally we would just extend the area where we expect a lot of rainfall to occur. So there's a question with regards to the air quality data. So the air quality observation data is open to the public. It's we've got a SAQUIS, SAAQIS. So there is a website that is available where all that data is completely open. Do we have any collaboration with IGAD countries? At the moment, we don't really have any active collaboration, but I recently attended a conference that was hosted with ICPAC. ICPAC is the Regional Specialized Meteorological Center. It is an of the IGAD countries. So we are hoping to get some more collaboration with those countries, and there has been interest from Ethiopia indicating that they would like to know more from us. They want to deploy radars, and in South Africa we have a lot of radars, so they want to get to collaborate with us on that. So machine learning, we are hoping to use some machine learning when it comes to our post-processing. So our to get products for the very short range forecast, we are hoping to use our radar, satellite, as well as NWP output to be able to get products for that very short range time scale. Then when it comes to the post-processing side as well, at the moment, we just give everything equal weight. So the hope is that using machine learning, we'll be able to pick out which is best and what are the best ways to be able to combine the data. Then again, with machine learning, so an area that is evolving is the use of machine learning in model development, and that is something that will inform the parameterizations. So these are processes that the models cannot resolve explicitly. So the hope is that machine learning can assist us in that area as well. Okay, so I'm just, so with regards to modeling, do you deal with numerical data only or images, and which one is easy to deal with based on models that you use? So with the models, we deal with data. So we are not really dealing all that much with images. But I mean, afterwards, we will produce the data, we'll use the data to produce images that the forecasters will use. So the forecasters would not deal with the actual numbers, they will look at the maps. Yes, so the question on fire, does the source do any wildfire spread modeling? Not the wildfire modeling spread as such. What we do is, based on the model output, we do provide a fire index. So you would have seen with some of our warnings, we do provide information on the fire index, but in terms of the fire modeling itself, we are not doing that. But when I showed the air quality information, you showed that I showed that we ran some biochemical fire model developed by NOAA just to determine what the concentration of different gases were that came from the fire. But then in terms of operationally, there's nothing that we are doing there. So the last one is, I'm doing research on evaluating and comparing machine learning models and empirical models for global solar radiation, but the data that I'm using has a lot of missing values. I want to know, why do we have, or what causes so many missing values when the data is recorded? That is a problem that we have as well as a country, as well as a continent, because if you have an observation network, you need to maintain it really well. And if the funding is not available to make sure that the observations are there and they are in place, you will get a lot of missing values. So the missing values are there because of challenges that are associated with funding to make sure that the network is well maintained. I think I've dealt with those, Christian.
Yes, thank you very much. I see that there's sort of there are another two questions in the chat, not in the question and answers. I think one of them you may have already answered, but one question is how much past information is used, for example, for a 48-hour forecast, for instance, so as the kind of initial conditions?
Yeah, so for numerical weather prediction, we don't really need a lot. So there's not a lot of training that is required. So it's a matter of knowing this is how gravity works, this is how the pressure gradient works. So it's really lots of physics that are there in the equations. So with initial conditions, right now we don't have a data simulation system, but for those that have, they would run maybe for 6 hours, just make sure that the model is aligned with what the observations are saying. But really up to about 6 hours, that's really all you will need for this type of short range forecasting. So there's not much training that we need. So with the training, you would need for, if you do, for example, seasonal forecasting, because you forecast deviations from an average. So for that, you do need to have a hindcast. So you need at least 30 years of simulation that you can calculate a deviation from.
Okay, thank you very much. I don't see that there are any more questions being asked. And on behalf of everyone who's joined today, thank you very much again for your time and a really wonderful overview of the really diverse computational and modeling work that is done. We very much appreciate it. Thank you very much. I just would also like to say on behalf of the organizers that we're sorry that the typical QMO space meeting that follows many of the seminars will unfortunately not be happening today, but next time maybe. Thank you very much for joining us. Thank you very much, Mary Jane. All of the best.
Thank you.
Thank you.
Thank you for inviting me.